Have you ever seen a lava lamp? These fascinating devices are not just a relic of the 70s, they are a perfect demonstration of a scientific principle that governs much of the natural world. A lava lamp is a groovy example of convection currents in action. When you switch on a lava lamp, the heat from the bulb at the bottom starts to warm up the wax inside. You see the blobs of wax moving up and down. This movement is not random, it's a beautiful dance choreographed by the laws of physics. But why do they do that? What makes the wax blobs rise and fall in such a mesmerizing way? It's all because of convection currents. Convection currents are a type of heat transfer that occurs in fluids, which can be liquids or gases. Convection currents happen when a fluid like the wax in a lava lamp is heated. As the wax at the bottom of the lamp heats up, it becomes less dense. The heated part becomes less dense and rises, while the cooler part sinks. This is because the molecules in the heated wax move faster and spread apart, making it lighter. This creates a continuous cycle of movement, much like the mesmerizing dance of the lava in the lamp. The rising and falling of the wax blobs is a perfect illustration of how convection currents work. The bulb at the bottom of the lamp heats the wax, causing it to rise. As it moves away from the heat source, it cools down and sinks back to the bottom, where it is heated again. This cycle continues as long as the lamp is on, creating a never-ending loop of rising and falling wax. It's not just a cool visual effect, it's a demonstration of a fundamental principle of physics. Convection currents are not limited to lava lamps. They occur in nature as well, such as in the atmosphere, oceans, and even inside the Earth. In the atmosphere, convection currents help to form weather patterns and influence climate. In the oceans, they drive currents that distribute heat around the globe. Inside the Earth, convection currents in the mantle are responsible for the movement of tectonic plates, leading to earthquakes and volcanic eruptions. So, the next time you watch a lava lamp, remember that you're witnessing a small-scale version of a process that shapes our world. It's a beautiful reminder of the power and elegance of nature's forces. Convection currents are like a natural engine that moves heat around. Imagine a pot of water on a stove. The burner heats the water at the bottom. This hot water becomes less dense and rises to the top. Meanwhile, the cooler water at the top is denser and sinks to the bottom. This cycle of rising and sinking creates circular currents within the pot, distributing the heat throughout the water. This is convection in action. Convection currents are everywhere in nature. They are the invisible forces that shape our world, influencing everything from the weather we experience daily to the deep ocean currents that regulate our planet's climate. These currents are driven by the simple yet powerful principle of heat transfer. They drive our weather patterns. When the sun heats the Earth's surface, it warms the air above it. This warm air, being less dense, rises into the atmosphere. As it ascends, it cools and eventually sinks back down, creating a cycle. This cycle is what we know as convection currents. Warm air rises, creating areas of low pressure, while cool air sinks, creating areas of high pressure. This difference in pressure is what generates wind. For instance, when you see a hot air balloon rising, it's because the air inside the balloon is warmer and less dense than the surrounding air. This movement of air causes wind and helps distribute heat around the globe. Wind turbines harness this energy, converting the kinetic energy of moving air into electricity. The rustling of leaves, the gentle breeze on a summer day, and even powerful storms are all manifestations of these convection currents at work. Ocean currents are also driven by convection. Just as the air moves due to temperature differences, so does water. The sun heats the surface of the ocean, causing the warm water to rise and move towards the poles. Warm water from the equator rises and flows towards the poles, while colder, denser water from the poles sinks and flows towards the equator. This movement creates a continuous loop, known as the thermohaline circulation, which is crucial for distributing heat and nutrients across the globe. This global conveyor belt of ocean currents plays a crucial role in regulating Earth's climate. It affects weather patterns, marine life, and even the carbon cycle. Without these currents, our planet would be a very different place, with more extreme temperatures and less hospitable environments for life. Understanding convection currents helps us appreciate the delicate balance that sustains life on Earth. Believe it or not, convection currents are also responsible for the movement of Earth's tectonic plates. The Earth's mantle, the layer beneath the crust, behaves like a very viscous fluid over long periods. Heat from the Earth's core causes the mantle material to rise. As it rises and cools, it becomes denser and eventually sinks back down. This continuous cycle of rising and sinking mantle material creates convection currents that drag the tectonic plates along with them. Section 5. Convection currents in our homes, keeping us warm and our computers cool. Convection currents are a fascinating phenomenon that play a crucial role in our daily lives. They are responsible for the distribution of heat in various environments, including our homes and electronic devices. Understanding how these currents work can help us appreciate the technology and systems that keep us comfortable and our devices functioning efficiently. Convection currents are not just found in nature, they are also hard at work in our homes. When we think about staying warm during the colder months, we often rely on heating systems that utilize convection currents to distribute heat evenly throughout our living spaces. This ensures that every corner of our home remains cozy and warm, no matter how cold it gets outside. Radiators, for example, rely on convection to heat our rooms. When a radiator is turned on, it heats the air around it. This warm air then rises because warm air is less dense than cool air. As the warm air rises, it creates a space for cooler air to move in and take its place near the radiator. The radiator heats the air around it, causing it to rise. This process is continuous, with warm air rising and cooler air descending to be heated by the radiator. This cycle ensures that the room is heated evenly, providing a comfortable environment for everyone. This rising warm air displaces the cooler air, which then gets heated by the radiator. The cooler air, being denser, moves downwards and gets heated by the radiator, continuing the cycle. This natural process of convection ensures that the heat is distributed evenly throughout the room, making it warm and comfortable. This creates a continuous cycle of air circulation, distributing heat throughout the room. The efficiency of this process is what makes radiators such an effective means of heating. By understanding the principles of convection, we can better appreciate how our heating systems work to keep us warm during the colder months. Similarly, convection currents are used to cool our computers. Just as we need to stay warm, our electronic devices need to stay cool to function properly. Computers generate a lot of heat when they are in use, and if this heat is not managed properly, it can lead to overheating and potential damage to the components. To prevent this, computers are equipped with cooling systems that utilize convection currents. Fans inside the computer case help to move the warm air away from the components and replace it with cooler air from outside the case. This continuous flow of air helps to keep the internal temperature of the computer at a safe level. The heat generated by the computer components is transferred to the surrounding air, which is then expelled by the fans. This process ensures that the components remain cool and can operate efficiently. Just like in our homes, the principles of convection are at work, helping to maintain a stable and comfortable environment for our electronic devices. In conclusion, convection currents play a vital role in both keeping us warm and our computers cool. By understanding how these currents work, we can better appreciate the technology and systems that make our lives more comfortable and our devices more reliable. Whether it's the warmth of our homes or the efficiency of our computers, convection currents are an essential part of our everyday lives. Section 6. The significance of convection currents, shaping our world. Convection currents are essential for life on Earth as we know it. They regulate our climate, drive our weather patterns, and shape the very ground we stand on. Understanding convection currents helps us predict weather patterns, understand geological processes like earthquakes and volcanoes, and even design more efficient heating and cooling systems. They are a fundamental force of nature that plays a crucial role in shaping our world. Section 7. Conclusion: Convection currents, the unseen force that moves our world. Remember the lava lamp? It's a fun and mesmerizing way to visualize the power of convection currents. From the depths of the Earth's mantle to the air we breathe, convection currents are constantly at work, transferring heat, driving our weather, and shaping our planet. Section 8. Questions and answers. Test your knowledge about convection currents. So, how much did you learn about convection currents? Let's test your knowledge with a quick Quanda session. Question 1. What causes convection currents? Question 2. Can you name 3 examples of convection currents in nature? Question 3. How are convection currents used in our homes? Section 9. Glossary of terms. Understanding the language of convection. Convection, the transfer of heat through the movement of fluids. Density, a measure of how much mass is contained in a given volume. Tectonic plates, large, moving pieces of the Earth's lithosphere, which is the crust and upper mantle. Mantle, the layer of Earth between the crust and the core. Viscous, having a thick, sticky consistency between solid and liquid.